Welcome to the Ready Academy. Tools for teaching, tools for learning, tools for life. In this video book, we cover the 4 laws of thermodynamics. This content was produced with AI assistance and reviewed by a human instructor. We'll continue with the first law, conservation of energy. Internal energy and its bookkeeping. The internal energy U of a system is the total microscopic energy stored within it. Kinetic energy of molecular motion, potential energy of intermolecular bonds and fields, and so on. Internal energy is a state variable. It depends only on the current state, not on how the system arrived there. Energy can cross the boundary of a closed system in exactly 2 ways: as heat Q, transfer driven by a temperature difference with no organized macroscopic motion, and as work W, transfer associated with organized displacement against a force. The first law is the energy ledger. First law of thermodynamics. For a closed system, the change in internal energy equals the heat added to the system minus the work done by the system. Equation 3. Delta U equals Q minus W. Delta U is the change in internal energy of the system, measured in joules. Q is the heat transferred to the system, in joules. And W is the work done by the system on its surroundings, in joules. Figure 7. A diagram illustrating the first law of thermodynamics for a closed system. At center, a rectangular region labeled System encloses the label Internal Energy, U. A dashed boundary line surrounds the system. On the left, a wavy arrow labeled Q, Heat In, crosses the boundary into the system. On the right, a straight arrow labeled W, Work Out, crosses the boundary out of the system. Below the diagram, the equation delta U equals Q minus W appears, with each symbol annotated to its corresponding arrow. This is equation 3, written in the physics and engineering convention, in which W denotes work done by the system on the surroundings. A positive W corresponds to the system pushing outward. For example, a gas expanding against a piston. A note on conventions. The IUPAC chemistry convention writes the first law as delta U equals Q plus W, with W defined as work done on the system. The IUPAC Gold Book entry for internal energy states it as quantity, the change in which is equal to the sum of heat, Q brought to the system in work, to W performed on it, delta U equals Q plus W. Both forms describe identical physics. They differ only in the sign assigned to W. Whichever convention you adopt, write it explicitly at the top of your work and stay with it. We use equation 3 throughout this chapter. The first law is the conservation of energy, restated for systems that exchange heat as well as work. James Prescott Joule's paddle wheel experiments in the 1840s, which we describe below, were the experimental cornerstone. Why perpetual motion of the first kind is impossible. A perpetual motion machine of the first kind is a hypothetical device that produces work indefinitely with no energy input. Such a machine would create energy from nothing in violation of equation 3. Centuries of unsuccessful attempts, overbalanced wheels, closed-cycle watermills, magnetic engines, are now understood not as failures of cleverness, but as a direct consequence of the first law. Pressure-volume work. For a gas confined by a movable piston, the work done by the system in a quasi-static expansion from volume 5, sub 1 to V sub 2 is the area under the curve on a PV diagram. Equation 4. W equals the integral from V sub 1 to V sub 2 of P dV. P is the pressure in pascals, and V is the volume in cubic meters, with V sub 1 and V sub 2 the initial and final volumes of the gas. Integrating the pressure over the swept volume gives the total work done by the gas on the piston. This is equation 4. Figure 8 shows why. Figure 8. A pressure-volume diagram with pressure on the vertical axis labeled P and volume on the horizontal axis labeled V. A smooth curve labeled process path runs from the upper left point labeled P sub 1, V sub 1, downward and to the right to a lower point labeled P sub 2, V sub 2. The region under the curve, between V sub 1 and V sub 2 on the volume axis, is shaded and labeled W, equals the integral of PdV, indicating the total work done by the gas during expansion. To the right of the diagram sits a small piston and cylinder icon, with an arrow pointing outward from the piston head, indicating outward motion during expansion. For an expansion, where V sub 2 is greater than V sub 1, W is positive. The gas does work on the surroundings. For a compression, W is negative. The surroundings do work on the gas. Because the integrand is the actual pressure inside the gas at each instant, equation 4 holds strictly only for quasi-static processes. For fast non-equilibrium expansions, one must use the external pressure at the piston instead. Isothermal expansion of an ideal gas. 1 mole of an ideal gas expands isothermally and reversibly at T equals 300 Kelvin, from V sub 1 equals 1.00 liters to V sub 2 equals 2.00 liters. Find Q, U, and delta U. Step 1. For an ideal gas, internal energy depends only on temperature, so delta U equals 0 in any isothermal process. Step 2. By equation 3, Q equals W. Step 3. The ideal gas equation gives P equals nRT over V. Substituting P equals nRT over V into equation 4, we find W equals the integral from V1 to V2 of nRT over V dV. Thus, the integral reduces to W equals nRT times the natural logarithm of V2 over V1. Step 4. Plugging in. W equals 1 mole times 8.314 joules per mole per Kelvin times 300 Kelvin times the natural log of 2, which gives 2,494.2 joules times 0.693, or approximately 1,729 joules. Result, W equals Q, approximately positive 1.73 kilojoules, and delta U equals 0. The gas absorbs about 1.73 kilojoules of heat from the surroundings and does an equal amount of work on the piston. Joule's paddle wheel and the mechanical equivalent of heat. In the 1840s, James Prescott Joule built a beautiful experiment to settle a long debate about the nature of heat. Falling weights drove a paddle wheel inside an insulated barrel of water. The descent of the weights was a precisely known amount of mechanical work, and the rise in water temperature was a precisely known amount of heat. Their ratio was the same regardless of how the work was delivered: paddles, friction, electrical heating. Heat, Joule showed, was not a fluid but a form of energy. Figure 9, a schematic of Joule's paddle wheel experiment. On the left, 2 cylindrical weights hang from cords that pass over a pulley mounted on a vertical support. The cords connect to an axle that enters through the lid of an insulated cylindrical barrel. Inside the barrel, a paddle wheel with multiple vans is mounted on the axle and submerged in water. A thermometer protrudes through the lid into the water. Downward arrows on the weights indicate their slow descent. A curved arrow inside the barrel shows the paddle wheel rotating. Labels read, weights, known descent equals known W, pointing to the hanging masses, insulated barrel around the cylinder, paddle wheel pointing to the vanes, and thermometer, measures delta T, pointing to the thermometer. The modern conversion factor, fixed by definition. Equation 5. 1 thermochemical calorie equals exactly 4.184 joules. This is equation 5, where cal sub Th denotes the thermochemical calorie. The slightly different international table calorie is defined as exactly 4.1868 joules. Both are non-SI units retained for historical compatibility. Joule's 1849 paddle wheel measurement, communicated to the Royal Society by Faraday on the 21st of June, 1849, gave 772 foot-pounds per BTU, equivalent to roughly 4.155 joules per calorie, about 0.7% below the modern value of 4.184 joules per calorie. That precision, achieved in a Manchester cellar by a brewer-turned-physicist, is one of the great experimental performances of the 19th century. Try it. A 100-gram block of metal is dropped from a height of 2.0 meters into an insulated container holding 200 grams of water. Assuming all the gravitational potential energy ends up as internal energy of the water, what temperature rise does the water experience? Use G equals 9.81 meters per second squared, and the specific heat of water 4,184 joules per kilogram per Kelvin. Pause the video now and give it a try. That wraps up the first law, conservation of energy. Next up, Section 4, the second law, direction and entropy. If you found this helpful, like and subscribe and support the channel.